Yeah, hi, I'm Thomas and welcome to this talk where I ask the question, can truly nonlinear dynamics be linearized? This is joint work with Florian Kogelbauer from ETH Zurich, and you can also find the details and technicalities in our joint publication appeared in Nonlinear Dynamics earlier this year. So linearization. For linear systems, we do have explicit solutions. We can exploit powerful principles such as superposition, and we have a huge toolbox of algorithms available at our disposal to employ for linear systems. This is certainly not the case for nonlinear system, and a strategy to make some of this knowledge available for the from the linear world available for the nonlinear world is linearization. And linearization has been around for decades, and classical results are local in nature, for example, Hartmann-Grubman theorem or Sternberg linearization. Those have been extended to the basin of attraction for hyperbolic fixed points, and recently there has been the promise of the Koopman operator, which promises a linearization of any nonlinear system via infinite dimensional linear system. However, the limitations of this promise of the Koopman operator have been pointed out recently in various publications. And more specifically, has been pointed out that it is challenging for the Koopman operator to linearize dynamics with multiple coexisting steady-state solutions. So this motivates our questions: can now truly nonlinear dynamics be linearized? To further motivate the topic of truly nonlinear dynamics, I brought along a motivational example here, two-dimensional system, and we can plot the phase plane of the system. And we can also see that this system has four fixed points. And we can see that the first coordinate needs to decay to 0, and we can have fixed points, non-trivial fixed point for the second coordinate at 0, pi over 2, pi, and 3 pi over 2. The fixed points at pi over 2 and the fixed point at 3 pi over 2, those are stable. So this is an example of a system I'm talking about, truly nonlinear example, where we have a coexistence of multiple steady-state solutions. And this has been challenging to proved challenging to linearize. However, now if I point out the equivalent linear system is the 2D stable node. And if you ask what is the connections between those two systems is polar coordinates. So now if you look at the stable node in polar coordinate, it becomes the rise of these four fixed points become intuitively clear. So for all initial conditions here on the right hand side, they generally decay along the slow stable direction y1. So y1 has a decay of lambda 1. Lambda 1 is less than 0, so it's a decay, but it's greater than lambda 2. So y1 is the slow stable direction. And for all these initial conditions, the x1, so this is the radial coordinate, goes to 0. So this is the fixed point here on this line, x1 equal to 0. However, we see that the angle approaches along because the initial conditions decay along the slow stable directions y1. The angle x2 approaches the value of pi over 2. So this gives rise to this fixed point here on the left hand side. Similarly, all trajectories starting on the left hand side of the plane here, decaying along this stable directions, they give rise to the angle of 3 pi over 2, this stable equilibrium. In addition, we have the fast stable directions, which are the fixed points at 0, so angle 0 and angle pi. However, those are unstable. So this motivates our search for linearizing transformation for truly nonlinear dynamics with coexisting fixed points. So our approach will be, we have a nonlinear system with a certain nonlinear phenomena, and then we're trying to come up with an equivalent linear system which mimics the nonlinear behavior which we have observed most closely. And then if we do have a reason to believe, so we know that those are in some sense equivalent, we can learn a mapping which takes us from the nonlinear world to the linear world, and also vice versa, we can think about a mapping taking us from the linear world to the nonlinear system. And in the previous slide, in the previous motivation example, those transformations were just simple polar coordinates. It's not going to be always that easy, and so that's why we approximate our mappings in this talk now with neural networks. So we do have a reason to believe that those mappings exist. We can approximate them with universal function approximators such as neural networks. And the first system studied is the nonlinear pendulum. So this is the phase plane of the nonlinear pendulum. And if you think about a linear equivalence, something that mimics this phase space very closely, a trivial or like an obvious choice is the linear oscillator. So this has also just closed phase space trajectories as the nonlinear pendulum, and we can easily think about a mapping us from this orbits from the nonlinear pendulum in the orbits of the linear oscillator. However, one needs to be a little bit careful, because the frequency of the nonlinear pendulum is, of course, depends on the initial condition. So, addition to learning the mapping from the pendulum, from the phase space of the nonlinear pendulum to the linear oscillator, we also need to learn the initial dependent period, and then we need to massage. We need to transform or scale the angular coordinate of the linear pendulum with the nonlinear period to correctly reconstruct trajectories of the nonlinear pendulum. And this works quite well. So this is the phase space of the transformed linear oscillator. Those are time series of the linear oscillators. We can clearly see that different frequencies arise here. And if we compute the error between the transformed linear oscillator and the nonlinear pendulum, we see that this error remains below 5%. So if we now look a bit closer at our approach, we can see that any linear equivalent of the form with any frequency would have worked in our approach. And this gives us a glimpse on the infinite dimensional Koopman operator for the pendulum, and in the language of the Koopman operator, what we have approximated, we have found a two-dimensional invariant subspace of this Koopman operator, the generally infinite dimensional Koopman operator. And therefore we can also, for example, now out of our approach, we can deduce and plot, for example, Koopman eigenfunctions. As a next system, we have looked at the bistable Duffing oscillator, which has, again, families of periodic orbits. So this is the phase space. But in addition to the pendulum, we only had one family of periodic orbits. Now we have three families of periodic orbits encoded in these colors. And before working with this system, we have extended this system with the trivial dynamics. So this trivial dynamics now separates those three family of periodic orbits into separate planes. And now we can think about a mapping of this nonlinear system to the extended linear oscillators, which is also just the linear oscillator as we had before. But we again have this extension by a trivial coordinated, which then takes care of these three individual families of periodic orbits. And those two systems, the nonlinear extended system and the extended linear oscillator, they look very similar. And then we can also see that our approach now we have presented earlier between those systems, extended by one trivial direction, should work in a similar way. And it turns out that this is the phase space of the reconstructed linear system. So the linear system here features three different families of periodic orbits. We have time series of the linear system, and the error remains about less than 0.5%. As the next system, we have looked at the Van der Pol oscillators. So this is a hallmark of a nonlinear behavior where we have limit cycle oscillations, and we have embedded this system in the linear limit cycle. So the limit cycle is linear and polar coordinates. And if we then plot this in Cartesian coordinates, we end up with a limit cycle. And then we can envision that there's a mapping between those two dynamics. And this can be learned. So this is here the phase space of the linear and the nonlinear system. So the nonlinear system is the full lines, and the linear system is the dashed dotted lines. So we see some discrepancies. However, the error norm primarily remains relatively small, below 5%, except for this one trajectory here in blue. And if we look closely here at the time series, we see that the reconstructed dynamics, so the dashed dotted, the linear dynamics, lag a little behind compared to the full nonlinear dynamics. The orbit reconstructed by the linearization matches quite well. If you look here, the orbit is traced pretty well. However, the linear dynamics seem to settle with a little time lag here. But we envision, if we use more powerful neural networks, that this error can be reduced. As a last example, we have looked at force-damped vibrations. This is a force-damped Duffing oscillator for parameter values where we have two coexisting steady-state solutions. And to embed this system, we have extended the system, so first by a phase variable here, and then also by a force variable x4 here with trivial dynamics to encode the two different steady-state solutions. And this can be equivalently embedded in the linear equivalent damped oscillators, where we have a phase variable and also the trivial coordinate to account for the two steady states. And we can again approximate the mapping, and then if we now transform the linear system back to the nonlinear world, we see that we can indeed observe a decay to two different steady-state solutions. So green are linear trajectories, transformed trajectories of the linear system decaying to a different steady-state solution compared, where blue are other trajectories of the linear system, transformed linear system, decaying to a different solution. And we can clearly see it here, the trace of two different steady-state solutions. And the error again remains bounded by about 5%. So summary, I have shown you linearizations of systems where we have coexisting steady state, where we had limit cycle, then we had families of periodic orbits, and also multiple families of periodic orbit. The strategy was always we come up with a well-chosen equivalent linear system, and then we approximate the mapping between the linear and the nonlinear setting by using neural networks in our approach. The examples discussed here were the pendulum, the Duffing oscillator, and the Van der Pol oscillators. So if you want to learn more, you're welcome to refer to this, to read in this publication. For the future directions, we envision to work on parameter dependencies and ultimately on chaos, so trying to linearize chaotic dynamics. Moreover, we'll be interested in working with experimental data. Thank you very much for listening. If you have any questions, feel free to reach out. Thank you very much for listening. Goodbye.